All right, welcome to class. We are looking at week 7, which is applications of differentiation. So if you have, to get a book in front of you, you need book 7. This is for week 7, rather. This is book 6 for week 7. Welcome to class. We are going to be looking at applications of differentiation together. So we're applying, looking at applications of the gradient function. So let's just remember, first of all, what is the gradient function? The gradient function, also called the derivative function, we feed it values of x, and it spits out the gradient of the tangent of a particular function, f at x. So our gradient function, if we call our gradient function f dash of x, we feed it, it will relate to some parent function f at x. We input x values, and the gradient function will spit out the gradient of the tangent on the function f at x at that particular x value we feed it. If your parent function is called y, we would refer to the gradient function as dy dx. Okay? All right, so let's look at our first application of differentiation. And in this first application, we're going to look at looking at the parent function and then considering what its gradient function looks like graphically. So instead of doing the algebra, which you would have looked at in book 5, the algebra of differentiation, we're going to look at the graphs of a derivative. So here we've got the graph of a quadratic. It's y equals 3x squared plus 4x plus 1. And we're going to compare it to its derivative function. And we can look at, we know that we can differentiate a polynomial, so we can find its algebraic derivative, and it would be 6x plus 4. So let's compare the two and look at some special features. So we can see that on the quadratic, the stationary point corresponds to a point where the gradient of the tangent goes to 0. Okay? So this is my graph of y, and this is my graph of my derivative. The derivative any time y, or the parent function, has a stationary point, the gradient function's graph should have an x-intercept, because the gradient should take the value 0 there. The next thing I want to consider are the regions of the graph. So you can see if you drew a gradient of, a tangent to any point to the left of that stationary point on the graph of y, you would have negative gradients. You can draw at any point and you'll find those gradients are negative, and they keep decreasing in magnitude until they get down to completely flat gradients. So to the left of that stationary point, the gradient functions should be negative. So you can see the region, the whole drawing should be down here. Likewise, to the right of the stationary point, if you start trying to draw gradients of the tangents at any point, those gradient of the tangents should be positive. So when you look at your gradient function, the region, that entire gradient function should be in the region above the x-axis. Finally, this equation was fairly straightforward purely because the parent function was a quadratic, so we kind of know that our derivative needs to be linear, just using our algebraic sort of sense and rules. So this made this a slightly easier question because we could kind of predict the nature of the derivative, that it needed to be linear. But just to look at its shape and what's happening, I'm just going to delete some of these drawings here. So y is the straight line looking like this. If you look to, we've already determined that the gradients need to be negative to the left of the stationary point, but you can see the gradient starts strong negative, very high magnitude negative values. So down here are strong negative values. Their magnitude is decreasing. All right, we say the numbers are actually increasing because they're going from, say, let's say this is, strong gradient, say -3, and then they're going to flatter and flatter gradients like -2, -1, -0.5. They're flattening out. The gradients are flattening out till they actually reach completely 0, completely flat gradient. But the numbers are getting smaller. The magnitude is getting smaller, though we say the numbers themselves are going from, say, a strong negative, which is like -10, to -6, -5, -4, -3, -2, -1, all the way to 0. And they're flattening, so they're actually, the gradients are increasing in value because they're going from strong negatives to lower negatives, but their magnitude is decreasing, they're getting flatter. So we're looking at strong negatives to low magnitude negative gradients. And then over here, we're starting quite flat positives, and then they're getting stronger, stronger, stronger. So they are increasing in values. They're all positives. They're always above the x-axis to the right of this stationary point, and they're getting stronger, stronger, stronger. All right. So when we're looking at a parent function and we're trying to draw its gradient function graph, there's really 3 things you want to do. The first thing is any stationary points. You want to consider any stationary points. They will be an x-intercept on the gradient function. The second thing I would do is consider regions of the graph. So look to your parent function and look at which regions the gradient function is positive and which region it's negative. So consider your stationary point and consider whether the gradient is positive or negative to the left and right of that. And that will give you the regions, which I drew on as little hashtags. If you need to go into more depth than that, you then consider the magnitude. What are the gradients doing? Are they getting steeper or flatter? Are they increasing in magnitude or decreasing? And that then helps you to draw your drawing. Above all, if you can identify the parent function, then you can identify the specific derivative function, and you don't really have to use graphing techniques. You can algebraically find the derivative, and you can then just graph it. So let's take a look. Let's take a look at some questions where we're going to be asked to draw the gradient function given the parent function. And some small notes on the shape of the derivative function. Now, if you need to do an accurate plot and you don't know the rule of the parent function, so you can't just algebraically differentiate it, and you need to find a pretty precise drawing, you can actually draw gradient of the tangents on the graph of the parent function and try and estimate the size of the gradient function at those values. And that will give you a pretty precise drawing. Now, in practice, this style of question tends to be multiple choice tech active, so you usually don't need to actually be that precise. Usually you're just picking between some values. But let's look at some very precise graphs. A couple of quick notes, just summarizing. If the tangent to the curve is parallel to the x-axis, that means if we've got a completely flat gradient, we know the gradient is 0 at that point. That means the derivative at that point, particular point, is 0. And the gradient function will have an x-intercept there. If the tangent is parallel to the x-axis, so we've got something like this, we would say that gradient is infinite, completely vertical. It's got only rise, no run. We would also say this is undefined. So we would say the derivative is undefined there. Is undefined, okay? Now, you can see that the steeper the line, the stronger it is in magnitude. Okay, the greater the magnitude. So for example, the blue line's about 10, and the red line's about a gradient of 1. Okay, and this just mentions that if we are able to tell the exact rule of the parent function, then we can just find the gradient function algebraically. So for example, if we look at a parent function and it looks quadratic, we know that the derivative needs to be linear. So our gradient function graph should be linear, and it helps us to make a more precise graph. All right, so let's go right to a problem. So let's go through to question 2. Now this question is harder than you will probably get, because most of your questions of this nature will be multiple choice, and you just need to pick between the problems. All right, so for this question, we're given a parent function f at x, and it's been drawn for us below. And it's got a fixed domain of -3, 6. And this is probably an important point, because from book 5, which is our differentiation techniques, we learned that a function is not differentiable at its endpoints. So we know that we have to keep that in mind when we draw our gradient function. All right, so that's our parent function drawn in red. And our goal of the question is to sketch the graph of the derived function, or the derivative f dash x, and hence state its domain. Okay, so our goal is to draw the derivative function. And I actually might draw it up here just so I can stay on the same graph whilst I work. So I'm going to draw my derivative, and I'm just going to pick a different color so it's really distinguished from the parent function. So I'm going to draw the derivative function, the gradient function, in blue, and I'm going to call it dy dx. All right, so I'm going to start with the leftmost. You can see this is kind of made up of 3 separate little rules. We've got this one here on the left, defined between -3 and 0. We've got another rule between 0 and 4, and we've got a third rule between 4 and 6. So I'm going to start with the 2 linear bits. Any straight line only has a single gradient. The gradient is not changing. Every curve has a changing gradient, and that's really what defines it as a curve. So we can see that with the leftmost bit and the rightmost bit, they're both linear, so they both only have a constant gradient. All right, and we can actually determine it because we have a scale here. So let's just look at the leftmost bit and find its gradient. The gradient of that line, well, it rises 1, 2, 3 for a run of 1, 2, 3, 4. So the gradient of this bit here, the gradient is rise of 3 over a run of 3, rather. I counted wrong the first time. So we rise 1, 2, 3 units for a run of 1, 2, 3 units. So rise 3, run 3, it's positive gradient. The gradient is 1. So for that region between -3 and 0, there's a constant gradient of 1, and let's draw it on now. So we know that this height, if you have a ruler, please use a ruler. We know that the derivative is not defined at its endpoints, so those need to be open circles. I don't have a ruler, but use a ruler if you have one. So we know the gradient is equal to 1 in that region. It's just a constant flat line gradient. It's always 1, so that creates a horizontal line. All right, and with the open dots, because we've got an endpoint here, and we know that the derivative does not exist at endpoints, nor does it exist at cusps. So that's a sharp point there. So we've got to have open circles on either end. Now let's move to the third rule over here, because that's another straight line, so that'll be nice and easy. That means its gradient is always constant. It's just some constant number all the time. The gradient of the tangent on that point, at any point on that graph, is always the same. It's a constant number. So let's do that now. So let's count down. Let's use a graphical technique. So the gradient of part 3, I'll call it gradient 3, we go down 1, 2, 3, 4, 5, 6. So we go down 6 over a run of 1, 2. So 1, 2 units over. So that means we've got a gradient of -3. All right, so constant gradient of -3 all the time. You can see at this point, we've got a sharp point, so the derivative won't be defined there. It'll be open. And at this point, we have an open circle. Even if it was closed and it was an endpoint, the derivative would not exist at an endpoint. So we will keep that, preserve the open circle, and that goes to 6. So if you have a ruler, please use it to connect these dots. Vika will expect you to use a ruler for any linear graphs that they ask you to draw. So just make sure that that's drawn with a straight edge, if you can. I don't have one at the moment. All right, so now we need to do this little middle region. The easiest way to approach this problem will be to estimate that with a curve that we know. And to me, that looks quadratic. It could also be quartic, but it looks like a power function quadratic to me. So I'm going to estimate it with a quadratic. But before we do that, let's just use our little graphing techniques. We know the first thing that we can do when we see a curve and we want to draw its gradient function is we consider the stationary point. The stationary point here is at 2. We know the gradient of the tangent goes 0 there. So on the gradient function, that becomes an x-intercept. The next thing I need is just my regions. So I can see to the left of that stationary point, my gradients are negative. Draw the gradient of the tangent at any point to the left of that, that stationary point too, and you will see a negative gradient. So my region of my derivative should be down here. And likewise, go to the right of the stationary point at 2, and you can see if you draw the gradient of the tangent at any point to the right on that rule, that it's a positive gradient. So the region of that gradient function should be up here. If we were just estimating, we could start drawing a gradient of the tangent here and estimate where it is, but I'm going to use an approximation to that curve. So that red curve, the second rule there, which looks quadratic to me, I'm going to approximate it with a quadratic. So here I go. So I'm going to approximate it. I can see its intercepts are at 0 and 4. And so I'm going to approximate it. I'm going to say it might have a different dilation factor. So I've got, actually, I might use its turning point form. So I can see that the turning point lies at 2, -2. So I'm going to use this value here. So x minus 2 squared minus 2. So I'm going to approximate that little second rule of the hybrid function with x minus 2 squared minus 2. And I'm going to differentiate that now to find its derivative. So that's the gradient of the tangent at any point. That's using a little chain rule. So we've got 2 times x minus 2 to the power of 1 times by the derivative of the inside, but that's just 1. So this gives me 2x minus 4. And now that's a little straight line graph. I'm just going to draw it between the point 0 and 4. So at the point 0, which is where this little rule starts, 2 times 0 would be 0 minus 4. So the gradient function will be -4 for me. So I'm going to start that. It's an open circle because that's a cusp and it won't, the derivative won't be defined at sharp points. Likewise, I'm going to now test the value of my derivative at the value 4, which is the end of my rule. I've got dy dx equals, so at 4 we've got 2 times 4, which is 8 minus 4, so that's 4, positive 4. So we've got 4, which is up here. Now, that should not be closed like I've just drawn it. It should be open because, again, we have a cusp here, so the derivative will not exist. Now, if you have a straight edge, please connect with your straight edge. I don't have a straight edge at the moment, so I'm just going to do my best, but Vika would take a mark away from me. And I'm going to mark that in blue, actually, because my final function I said was in blue and was dy dx. That is our final function. So marked in blue, we have the derivative function dy dx. And that's the end of the question. Now that's a lot harder than you're actually going to encounter from Vika. They're mostly going to make these multiple choice, which is a lot easier because you're just looking for the key features, really. Here we actually had to find and approximate that little middle function to get a nice accurate derivative graph. Let's move to question 3. So moving to question 3 now. Here we've got the graph of a function f at x, and this is not a graph we know and recognize. So this makes this kind of a nicer question, purely because we can only use graphing tools. We don't know how to estimate this curve. It's not one of our tech-free graphs that we're expected to know how to draw. We're going to do this as an exam 1 question. But this is a lot harder than you'll actually get exam 1. Often this will be an exam 2 multiple choice, and we'll have lots of options, and we'll just pick the one that has the features we're looking for. So this is the parent function f at x, and the instruction is, on the axis below, sketch the graph of the derivative f dash x. So we're trying to sketch the gradient function, and then we have another instruction as well. So let's start with the first instruction. We want to sketch the derivative first. I'm actually going to do it on this graph just so I can still see it, because if I browse down here, I will not be able to see my parent function, which I need to see. So let's look at this. So in red, we've got the parent function y, or actually it's f at x. And in blue, I'm going to sketch our gradient function, which is f dash x. All right, so I'm going to start with the most simple feature, which is the stationary point. If you examine the red curve, we have one stationary point, and it's located right here. So I know on my derivative function, the gradient at that point will be 0, so the derivative function has an x-intercept there. So I'm going to draw that on right away. The next thing I take care of are my regions. So if I were to draw a gradient of the tangent at any point in this, in the region to the left of that stationary point, I would see that those gradients were negative. So they're all negative to the left of that stationary point. So I'm going to do my regions in green here, just with little hashtags. So I know between 0 and 2, that the derivative function will lie below the x-axis. Likewise, to the right of the point, the stationary point 2, you can see that if you were to draw a gradient of the tangent at any point to the right there, they would be positive. They get a little flatter, they go steep, flat, but they're all positive to the right. So my region, the entire gradient function should lie above the x-axis to the right of the point 2. So I'm just going to put that with green, and I'm going to put that over here. So I've got my regions now. Now this graph is harder because it's not a graph that we know and recognize. There's no way to approximate it with a rule. So we're now going to have to just consider the magnitudes of the gradients. So I'm going to start here. And I can't quite draw a perfect straight line, but if you have a straight edge, you're going to actually be able to do a better job than I am. What I'm going to try and do is I'm going to try and draw a straight line right here and estimate the gradient of the tangent at that point there. So I'm trying to estimate the gradient of the tangent for myself right close to the value x equals 0. So I'm trying to estimate it. If you have a straight edge, you're going to do a better job than me, because I don't have a straight edge at the moment. So just using this orange graph, I'm going to try and estimate the gradient of the tangent right at that point x equals 0. So I can see that I'm going down. This is just an estimate, but for me, I'm going to estimate that first gradient of the tangent to be down 1, 2, 3. Whoops, 1, 2, 3, 4, 5. So down, I'm going to say it's down about 5. Over a run of about 1.25. Now, if you have your CAS, let's just estimate that value on the CAS. And this is just an estimate. It's kind of the best we can do because we don't have the equation of that graph. So I said it was about -5 on 1.25. So let's just estimate that number. So I'm getting an estimate of about -4. It's just an approximation. But that then means, if we go back to our question, if I'm drawing my gradient function, The steepest negative gradient happens right here, and I'm saying it's about -4. So I'm going to stick that on. I know it has to be an open circle because that's an endpoint, and the derivative doesn't exist at endpoints. If I look at the region between, you can see that draw the gradient of the tangent at any other spot between 0 and 2 on the parent function, and the gradient of the tangent is flattening. So it should be getting closer and closer, and then it eventually actually hits 0. So in this region, the gradient is flattening in some way. So it's slowly being connected like that in some way. But I'm going to leave it as dots until I get the rest of my graph sort of on. Now I'm going to examine the region to the right of the stationary point. And we already know that that region needs to be all positive gradients. But what we'll do now is we will consider the gradients, what they're doing magnitude-wise. So they're starting completely flat at 0, right there. Then they're getting steeper. They're getting steeper pretty fast, and for me, I'm just estimating this, but the steepest gradient looks to happen around right there for me. So I'm going to estimate that gradient now, and it's just an estimate, especially because I don't have a straight edge. It's going to be a huge estimate for me. So I'm just going to estimate where I think the strongest gradient happens. I'm estimating that it's about right there, and I'm just going to imagine drawing a gradient of the tangent to that spot. And I'm just imagining this. It's definitely an estimate. But right there, if I estimate that gradient, I'm going to say I rise 2 units, so 1, 2 rise, over a run of about 1.5. That's the same as 2 divided by 3 on 2, which is the same as 2 times 2/3. So we're getting 4 over 3-ish. Oops. So this is about, so if you want to see it on the CAS, this is about, if you go 4 divided by 3 on the CAS, this will just give us an estimate. So about 1.3-ish. Again, it's just an estimate. I wasn't able to use a ruler, so my estimate's probably not as good as yours. So we're doing a gradient of about 1.3 here. So I'm going to rise right here at the steepest point, what I consider to be the steepest point. The gradient function takes a value of about 1.3 for me. And for me, that's a maximum. Because at that point, you can see the gradients start to flatten. And then they get really flat. And they get to be asymptotic. So they get so flat, nearly 0. And now I'm just going to connect my dots with my blue. So my gradients should, you can see initially they're getting lower in magnitude, negative. Then they're going high. They reach their steepest gradient. For me, I've approximated the steepest gradient right there, which I approximate to be about 1.3. And then they're quickly flattening out. They're still positive, but they're getting so flat they're almost 0. Now towards that asymptote, we should make sure that the arrow doesn't look like it's going to slice the x-axis. It should just be approaching it, so it should be asymptotic. That was a really hard question because there was no way for us to approximate that rule, so we had to go purely just on gradient function graphing techniques. There is a little follow-up question. So it says, hence sketch the graph of g of x, which is the derivative of x for x greater than or the same as 2. Okay, so I'm going to do this final graph with the yellow highlighter, see how I go, if I can draw with it. So whenever x is bigger or the same as 2, this function g is just the derivative function. So I'm just going to draw over that, see if this works. Ooh, it's not liking that. I'll just use, I'll try and use a yellow colored pen. Oops, try again. All right, let's try this one, see if this works. So I'll do this bit in yellow. G of x is a hybrid function. It takes the rule derivative of f, which we drew in blue, whenever x is greater than or the same as 2. So let's just draw that now. So greater than or the same as 2, we're just taking this value here. But it takes negative f dash x when x is less than 2. We can see that negative is out in front of the function. Whenever you make the output negative, you're reflecting over the x-axis. So what it's saying is reflect that derivative graph, the gradient function graph, over the x-axis when x is less than 2. So that gives us this function here. It ends at about there. So this will, in yellow we have the graph of g of x. So I'll just color that on here. So on that same graph, we've graphed g of x and we've graphed the derivative of f dash x.